Well, greetings, mathletes, and welcome back. Today's lecture is actually going to be a little more procedural than the other ones we've had. And when I say procedural, it means that there's not as much creative thinking that you have to do. It's pretty much this is how you do a process. Now do the process. So it's pretty straightforward. And that process is polynomial division. And so we're going to look at it two different ways. We're going to look at it in terms of long division, which is very similar to how you do division with numbers. In fact, it's the same algorithm. You follow the same steps as you go through. The other one may be new to you, and that's synthetic division. And it's a little bit faster, but it only works in certain situations. So it has its limitations also. And then we're going to take a little look at what we do with those divisions and what do you do when there's a remainder and what does the remainder mean and all that kind of stuff. And the next lecture, we're going to be looking at how to graph rational expressions. And rational expressions are a polynomial divided by a polynomial. So it leads right in. So we need to understand how to divide these things if we're going to be able to graph these things. So without any further lip flapping, let's go ahead and get started. Okay, so to start off, I want to look at just a regular division problem. So let's say I have 11 divided into 187. Okay, so, if we think about what we're supposed to be doing here, you would take the 11, you want to see how many times it fits into 18, right? Let's see here, it's going to fit in one time, and then I would multiply the 11 by whatever I have up here and subtract it out, right? And that leaves me with a 7, and I'd bring this 7 down. And I ask myself the same question. How many times does 11 fit into 77? And it fits in 7 times. 7 times 11 is 77, and I subtract it, and that leaves me with a remainder of 0. Okay, so that's standard division. Now, let's look at the following polynomials. Let's say, and I just want to point out that this gets written several different ways, so I'm going to write it the different ways. Actually, switch colors. Let's say I have x squared plus 8x plus 7, and I want to take that and I want to divide it by x plus 1. Okay, you could also see this written this way. Right, and in this form, it's a rational expression, and that's what we're going to be dealing with in the next section we cover. So this is going to be an important notation as well. The way we're going to work this out, though, is this way. So let's take a look at this. So we have, let's switch colors just so it stands out. We have x plus 1, and we're going to divide that into x squared plus 8x plus 7. Okay, so before what we did, we asked ourselves how many times 11 would fit into 18. Now, it's a little bit of a weird question to ask that same question about how many times x plus 1 fits into x squared plus 8. So we asked the question a little bit differently. We only concern ourselves with the first term. So I'm only looking at the x and the x squared for the moment. For the moment, I'm ignoring the 1. So I'm going to ask myself, what do I need to multiply x by to get an x squared? And the answer would be x. So I'm going to write that x down. Okay. Then I'm going to do the same thing I did before. I'm going to take this x and I'm going to multiply it by the entire x plus 1. Okay, so that gives me x squared plus x. That is not an x. Let's try that again. X squared plus x. Now, if you remember over here, we subtracted it. So really what we're doing is that. Okay, now that gets a little cumbersome because now you have to distribute the negative and everything else. So what I want you to be able to do here is actually do all those steps at the same time. So you're going to multiply this in, so that gives an x squared plus x, and I'm subtracting it. So I'm going to change all the signs as I multiply. So x times x is x squared. I'm subtracting it. X times 1 is X. I'm subtracting it. Now we just add straight down. Or if you want to call it subtraction, whatever. But sometimes the signs, the signs change. Sometimes these are pluses. So this will cancel, and that was our goal. And then 8x minus x gives me 7x. And then just like over here, right, I brought down the 7. I'm going to do the same thing. I'm going to bring down the 7, and then I'm going to ask myself, x times what will give me 7x? And the answer would be 7. So I'm going to, and it's a positive 7. So I'm going to write that down, and then I have to do the exact same thing. I have to multiply the 7 through and change the signs as I go. So 7 times x is 7x, but I'm subtracting it. 7 times 1 is 7, but I'm subtracting it, and I end up with a remainder of 0. Right? And if you have a remainder of 0, what that means is that you've just factored this polynomial. You've just found out that x plus 1 times x plus 7 is equal to x squared plus 8x plus 7. Right? You just found that out by doing this division, the same way you just found out that 11 times 17 is 187. Incidentally, I don't know if any of you noticed this, but if you let x equal 10, then this polynomial problem is the same thing as this addition problem, or this regular number problem, which I find very interesting. Okay, so let's look at another example. Okay, so let's go ahead and do that and delete that. Okay, so let's say I have, yeah, we'll do that one. X squared, where'd it go? There we go. X squared minus 6x, where'd it, plus 2, minus 2. So I have that, and I want to divide it by x plus 3. Okay, so we're just going to walk through the process again. Okay, so we want to write it all down. So we have x plus 3, and we're going to divide that into x squared minus 6x minus 2. And you'll see what I'm talking about with the signs here, that you just want to change the sign as you go. It doesn't always change them all to negative. Sometimes it changes them to positive because you're subtracting a negative. Okay, so we ask ourselves the same question. X times what gives me x squared? And the answer would be x. So I'll write down an x here. And then I'm going to multiply this through and change the signs as I go. X times x is x squared, and I'm subtracting it. X times 3 is 3x, and I'm subtracting that too. So you notice I distributed as I went. Now, if I add straight down, that cancels. Adding these together gives me minus 9x. See, that's what I was talking about, the signs. It's, even though it's subtraction, you're really just adding things. And then I'll bring down the minus 2 here. And I ask myself, x times what gives me negative 9x? And the answer is negative 9. So negative 9 times x is negative 9x, but I'm changing the sign. Negative 9 times 3 is negative 27, but I'm changing the sign. Right? And now if I add down, the 9x's cancel, but here I end up with 25 as a remainder. And so the question is, what do you do with the remainder? Right? Well, it's the same thing you do with regular numbers. You know, if I was doing 5 into 12, that goes in 2 times, and I have a remainder of 2. So if I really wanted to keep this mathematical in a form that I can use, I would take this 2 and put it over the 5. So this is 2 and 2/5. What's not written here is this is actually 2 plus 2/5. Right? It's just understood that when you write 2 and 2/5, that it's 2 plus 2/5 more. So we don't write it. But with polynomials, we have to write it. So we have 25, and just like we put the 2 over the 5, I'm going to put the 25 over the x plus 3. So this is plus 25 over x plus 3. So basically what we just did was we made a mixed number out of a polynomial, out of a rational expression, is basically what we did. right? So that's how you handle those remainders. There's actually other things we can do with those remainders too. That's the last thing we're going to cover today, and that's the remainder theorem. But yeah, this would end up being your answer. You'd have x minus 9 plus 25 over x plus 3, right? And that actually is a really, really handy form if you're going to be graphing this function. Right? That's a rational expression. That means it can be graphed. It's actually a lot easier. Well, you can get certain things out of this that you can't get out of the other form, basically, is the idea. So if you can convert them, you actually get a lot of information. So, and that's, again, that extra information is going to be in the next lecture. So in any case, let's take a look at another example, because there's a lot of little, a bunch of little things that happen with these that sometimes can mess you up. So we're going to take a look at a lot of those little things. All right. So let's suppose, we're walking down a dark alley and someone jumps out, hands us this division problem, and wants an answer, and they have a gun. Okay, so let's see what happens. Let's see if we live. Yeah, so if we're going to do long division on this, there's some things that are kind of interesting. You start to notice problems right away. If I try to work it out just the way it's written, right? I ask myself, okay, so x times what gives me x to the fourth? Okay, that's going to be an x to the third. And if I multiply that through, I get minus x to the fourth plus 2x cubed. And we have a problem. These will cancel, but those aren't like terms, right? And that's an issue, because if those aren't like terms, we can't put them together. We can't cancel anything out. So let's go ahead and start this over. There's a trick you can use to go ahead and walk around that problem. So we still have the x minus 2 here on the outside. But this, you notice what terms are missing. It's missing an x cubed, it's missing an x squared, and it's missing an x. So what we do is we put those in. And that way it keeps all of our place values. It's basically lining up place values is what you're doing. And if we can keep the place values lined up, that works out pretty good. So we rewrite this as x to the fourth plus 0x cubed plus 0x squared plus 0x, and it's minus 16. Minus 16. Oh, that's going to be a lot of work here. So let's go ahead and take a look and see how this works out now. So x times what is x to the fourth? That's going to give me our x cubed. Once again, my favorite rapper name. So that gives me a minus x to the fourth. And if I multiply the negative 2 times x to the third, then change the sign, I get plus 2x to the third. And you notice these are like terms now. So I have that lining up. So those will cancel, and I end up with 2x to the third. And I'm going to bring down my 0x squared. Right? So I'm still following the same procedure. Just bring down the next term and keep going. So let's see here. X times what is 2x to the third? Well, that's going to be positive 2x squared. So if I multiply that through, that'll give me 2x cubed, but I'm subtracting it. And then that's minus 4x squared, but I'm adding it because I'm changing the sign. Right? And so that cancels, and that leaves me with a 4x squared. Now I bring down my 0x, and I ask myself again, x times what gives me 4x squared? And it would be 4x, like so. And if I multiply that through, that gives me 4x squared, but I'm subtracting it. Change the sign. And then that gives me minus 8x, but that makes it a plus. right? So let's see here. That cancels, and this leaves me with 8x. And I'm going to bring down my minus 16 now. And x times, well, it looks like x times 8 will give me 8x. So that gives me minus 8x. And then that's minus 16, but I'm adding it. And that gives me a remainder of 0. So that means, now keep in mind, this is not a complete factorization, but it is a factorization. We have x minus 2 times x cubed plus 2x squared plus 4x plus 8. Right? Now, it actually turns out if you're trying to factor this completely, you have to factor this piece too. But you notice it really brings you, it drops it down by a degree every time you can divide something out. Because sometimes what happens is you can't factor something, but you figure out that something is a factor. So what you can do is divide it out like we just did, and then see if you can factor what's remaining, right? And we'll be doing some of that. Okay. Yeah, so we had a remainder of 0, so yeah, that's complete. All right, so let's look at the next example here. Okay, so our last example of long division here, we're going to do this. We got, well, actually, let's switch the colors. 6x cubed plus 7x squared plus 12x minus 5. All right, so there's our first polynomial, and we're going to divide that by 3x minus 1. Okay, so I want you to try this one on your own. See if you can follow. All the steps are exactly the same. Some of the parts look a little bit different, but they still handle the same way. So see what you can do with this. Go ahead and pause it here, and then we'll work it out together. Okay, so pause. Okay, I'm assuming you've paused it. So let's go ahead and take a look at the division. So let's see, we got 3x minus 1. And let's see here, that's going to be 6x cubed plus 7x squared plus 11. Oh, that's not 11, it's a 12. 12x minus 5. Okay, and then, yeah, so we're going to go ahead and work this thing out now. So again, we concern ourselves with the first terms here. So 3x times what gives me 6x cubed? And let's see, we need a 2, and then I need an x squared in there. So if I multiply that through, that gives me 6x cubed, but I'm subtracting it. And then minus 2x squared, but that'll make it plus 2x squared. All right, so that cancels, and this gives me 9x squared plus 12x, because I'm bringing this guy down. Now, let's see, 3x times 3x gives me 9x squared. So I'll multiply that through, and that gives me a minus 9x squared, and then minus 3x, but I'm going to make it plus 3x. Okay, now if we add straight down, those cancel. This gives me 15x, and I'm going to bring that minus 5 down, and we'll see what happens here. So 3x times, let's see, 3x times 5 gives me 15x. So that gives me minus 15x. And then 5 times negative 1 is negative 5, but we're changing the signs. And that means I have a remainder of 0, which means it goes in evenly. And what that means is both of these things are factors of that original polynomial. Okay, so good. Hopefully you got through that on your own without too many problems, and what you did in your work pretty much matched what I just did. So, and if not, I'm hoping you found the mistakes, right? Or at least identified where you're having issues. Okay, so that's long division, right? Long division, once you have the process for it, it's the same thing every single time. The things you have to watch out for is sometimes you have a coefficient out in front of the divisor. And the other thing is adding the zeros into the dividend to make sure you have all of the terms represented. Those are the two big things that catch people up when it comes to doing long division with polynomials. Now, the next thing we're going to look at is called synthetic division. And at least for the process of doing the division, we can just get rid of all the variables at the same time and work with the coefficients. So let's go ahead and take a look at that process, and we'll do some of the same problems so we can see you get the same answer either way. All right, so let's see what we got here. Let's go ahead and clear this off. Oops, let's try that again. No. There we go. All right. Okay, so let's say let's go ahead and take a look at synthetic division. Now, synthetic division, basically, well, let's start with looking at the problem first. So let's say we have x squared plus 6x minus 2, and I want to divide that by x plus 3. Okay, so here's the setup. So you start by making yourself a little box like this. Now, you look at what you're dividing by. Now, there's certain things that have to be in place. One, this has to be a 1 in front of the x for this to work. If it's any other number, you have to do some things to make it a 1. And as long as this is a 1, then this is the number you're interested in, and you take its opposite. Because actually what you're putting there is whatever makes this term 0, and x would be -3 to make this a 0. So that means we're going to put a -3 out here, right? And then across the top here, what I'm going to do is just write the coefficients of the dividend. So we have 1. Oh, I meant to switch colors, but okay. 6 and -2, right? And so, this is one of those things where it really is more or less a trick. There's not a lot of direct mathematics you get out of this other than you get a process completed. So this is how it works. So the first thing you do is take this leading coefficient and drop it straight down. Okay, that's always the first step. Then you take the divisor, the -3, and you multiply it by this 1, and you write it up here. So the next thing up here would be -3. And if we add this straight down, what I get is a 3, right? Okay, so now I'm going to do the same thing here. -3 times 3 gives me -9, and I'm going to write that there. You notice there's no sign switching, and it's because that's taken care of over here, right? I have a +3 here, so if I write a -3, it takes care of all the subtractions. Now, the last number we get here, -11, is our remainder. And so the way this works is this. This started out as an x squared, right? This was 1x squared. When I divide it, this becomes an x. And so this ends up being x plus 3 minus 11 over x plus 3, which is a very interesting result. Now, if we had done this using long division, just so we can compare things up, right, if I did the exact same division here, let's see, that's going to give me x, and so I have a minus x squared minus 3x, and so you can see the -3 here. And then I would say, okay, so I need let's see here, that's going to cancel. That leaves me with 3x minus 2, and so I need another 3 here, right? So that gives me +3, and then 3 times x minus 3x, and that gives me -9, and I get a remainder of 11, and so I have minus 11 over x plus 3. So you get the same answer both ways. You'll find that once you've done a couple of these, I put a lot of explanation in here, but once you've done a couple of these, they actually go really, really fast because it's just multiply, add, multiply, add, multiply, add over and over again. In fact, after the first step, you don't even really have to think anymore. You just keep following the multiply, add pattern. Okay, so let's try a bigger one this time. So let's go ahead and clear this off. Okay, so yeah, let's go ahead and try this one. We've already done this one once. And just so you can see that the same types of things happen. Okay, so if I want to divide this now, and I want to use synthetic division, let's see here. So here in the divisor, I have a 1 here, so that's good. I don't have to do anything else. And then I just want the opposite of this. So that's going to be a 2 up here. And now you notice I'm missing a whole bunch of terms, and that will throw synthetic division off. And what's worse is that if you don't add in the proper number of zeros, you won't even notice that you've done anything wrong, right? Because there's no context to this. So you have to have it set up at the beginning correctly. Otherwise, you're just going to blast through it and get the wrong answer. So you have to be real careful here. So we have an x to the fourth, and I know that's a 1, right? That was an x to the fourth. I need an x to the third. That's going to be 0. I need an x squared. That's also going to be a 0. I need an x, which is going to be a 0. And then I have my constant term, which is minus 16. Right? So we have a bigger process this time. All right, so let's go ahead and work this out now. Now, keep in mind that when you do this division, your answer is going to, this is an x to the fourth. When you divide it out, it's going to be an x to the third. The next column is going to give you an x squared. The next one's going to give you an x. It's always 1 degree lower than what you started with. And then our constant term, right? And the last part, constant term is going to be here. The remainder is going to be in the last column. Okay, so let's go ahead and do this. So if I bring this down, this gives me a 1. 2 times 1 is 2. If I add those together, 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8. 0 plus 8 is 8. And 2 times 8 is 16. And that leaves me with a remainder of 0, right? So remember that last column's our remainder. So this is 1x cubed. You don't have to write the 1. Plus 2x plus 2x squared plus 4x plus 8, right? So I'm just pairing up the coefficients I found with the terms that they have. Now, there's some other things about this, and I didn't say this before, but the divisor, when you're using synthetic division, the divisor has to be linear, okay? Right? And if the divisor is going to be linear, that means it's in some form ax plus b, right? What we're going to do to make sure a is 1 is we're going to factor out, what do you call it, b over a. So, or excuse me, we're going to factor out a, and that leaves me with x plus b over a. And then we can use this term because now this has a coefficient of 1. Okay, so, excuse me, let's go ahead and take a look at the next thing here. And, okay, so this last one I want to look at here gets a little squirrelier. So let's see here, plus 7x squared plus 12x minus 5, and we're going to divide that by 3x minus 1. Okay, so we have some issues here. First of all, if we're going to do synthetic division, that's not a 1, right? So what we end up doing is we go ahead and factor a 3 out of both terms. Whatever that leading coefficient is, I'm going to divide that out. So really what I'm doing is I'm going to divide this by 3. And what that makes it is x minus 1/3. Okay, so that is now in the proper form, even though it has a fraction. Now, you can't just divide the denominator of a polynomial without dividing the numerator as well, right? But we're going to save that for the very, very end, because the whole point of this is to be able to do the division first. So this is now this whole 6x cubed plus 7x squared plus 12x minus 5. We're going to divide this by x minus 1/3. Okay, so that means the outside is 1/3, right? Because I'm changing the sign. And I'm going to put in all my terms. Let's see, I'm starting with an x cubed. So that means that my answer is going to start with an x squared. It always drops by 1 degree as you do the division. So 6, 7, 12, and negative 5. Okay, so let's see. The first thing we're going to do here is we're going to just drop this guy straight down. So that's a 6. Now, 1/3 of 6, don't think arithmetic, don't think multiplying fractions. What's 1/3 of 6? It's 2. If you break 6 into 3 pieces, it's 2. So we'll write the 2 here, and then we'll add straight down again. That gives us a 9. And then 1/3 times 9 will give us 3. 12 plus 3 gives me 15, right? And then 1/3 of 15 is 5, and that leaves me with a remainder of 0. And I think this is one of the examples we did earlier too. Now, here's the issue though. We divided the top and bottom by 3, so we should get this back, right? We should get 6x squared plus 9x plus 15, and then we have a remainder of 0. But we haven't done this division by 3 yet. So what we have to do is divide this whole thing by 3. And basically what that does is this, right? We divide each of the terms by 3, and that's going to give me 2x squared plus 3x plus 5 as our final answer, right? And that should match what we did before. In fact, if we do it with long division, that's the answer you get right from the start. You don't have to adjust anything. So this is actually one of those cases where the long division is actually easier to do than the synthetic division. And you can see the potential here. If we got real lucky, all 3 of these numbers that we got come out to a whole number when we multiply it by 1/3. That doesn't always happen. Sometimes you end up adding fractions as you go, and that starts getting really, really painful. So, synthetic division has its limits. Long division actually will work on anything, not just the linear terms. And we might see some of that when we get to the graphing part. It might show up a little bit more. But nonetheless, this is the entire process for synthetic division. It's the same thing every single time. And I'll tell you this too. I just looked through your homework, and they actually don't have any examples where you have to do this. So this is getting you a little bit ahead so you can see some of the things you'll be doing in the future. I will say too, there is a way of doing synthetic division with quadratic terms, right? So you're dividing by a quadratic, so you have 3 terms there, but it's very, very messy. You end up having to have 2 columns you keep track of things in, and it's actually just easier to do the long division. It works out a lot easier. So I don't even bother going into that. Okay, so let's talk a little bit about the remainder theorem. Let's delete that. Okay, so let's say we have p of x, and p of x is some polynomial, right? And I'm dividing it by x minus c. Now, I'm simplifying this so that it fits our situation a little bit better, but this does get generalized. If the degree of p of x exceeds the degree of x minus c by exactly 1, right? So that means they just differ by by 1 degree. So if the denominator has a degree 2, the numerator has a degree 3. They just have to be one off of each other in general. But because we're only dividing by linear factors right now, that just means that the numerator is quadratic and the denominator is linear. Then P of C, so that means if I plug C into P, P of C is equal to the remainder of P of X divided by X minus C. So basically, this is a way of getting a hold of a value that may otherwise be more difficult to compute. That's really the whole idea here. So let's look at what that means. Let's actually take a look at an example. Basically means that the remainder you get when you divide is the same thing as plugging plugging the root of that factor into the function. So let's go ahead and take a look here. So let's say I have, and we've seen this one before. Let's say P of X is equal to X squared plus 6X minus 2. Okay, so that's a polynomial. We've actually used that in an example already. And I can say that, let's just say I want to figure out P of 3. Okay, now you could plug in 3. Right, you get 3 squared plus 6 times 3 minus 2. That gives me 9 plus 18 minus 2, which is 25. Right? No big deal. We got 25. Well, what they're saying is that if you plug in 3 and you get a 25, then when you take x squared plus 6x minus 2, which is P of X, and divide it by, let's see, we plugged in 3, it would be X minus 3. The remainder we get at the end should be 25. And so we're going to try that. And you can do it either way. You can do it as synthetic division, or you could do it as long division. It doesn't matter. In this particular case, synthetic division is probably quicker. Right? So that means I have a 3 on the outside because it's going to be the opposite of this. And then my coefficients are 1, 6, and negative 2. So let's see here. Let's see how this goes. So let's see. We get 1. And 3 times 1 is 3, so I'll write that down. That gives me a 9. 3 times 9 is 27. If I add those, I get 25, which is my remainder. The last term is always your remainder. And you notice these things match, right? And so that's basically what this is saying, is that if you want to evaluate a polynomial at a particular value, you can also just do the division and look at the remainder. And it ends up working out to be the exact same value. Actually, we don't see too many cases in this section where it's faster to do the division than just to plug it in. But there are cases like that. And so they do become rather important. The other thing, too, is if you're programming if you're actually using a computer and you're trying to program an algorithm for doing polynomial division, it's going to be a lot easier to plug. Oops, I was trying to highlight that. It's going to be a lot easier to program in synthetic division than it is going to be to plug in long division. And so that's another advantage, is that it's easier for a computer to do those things. So in any case, that pretty much wraps up what I wanted to talk to you about today. So we're going to be looking at graphing rational expressions next. I'm all excited. It's good, clean fun. So until next time, keep your pencils and your wits sharp.